Hello, welcome back to class, y'all. I've been having a lot of technical difficulties. Hopefully I can get those resolved and be able to get these videos rolling out more regularly. But first I wanted to provide a quick recap of where we left off. So I wanted to do a run through of the distributions to help y'all with your homework. So let's do that. First we had the binomial distribution, where we had a certain number, let's say n many independent trials each with probability of success equal to some number between 0 and 1, which we called P. And we've been shorthanding the probability of failure as Q, which just means 1 minus whatever P was, probability of failure. And then our random variable was counting number of successes. So then we finally got, okay, the probability of little x many successes was choose where the successes happen, so n choose x, and then if we have x many successes, there's probability of p for each one, so you get p to the x, and then the probability of failure, well, how many failures do we have? It's just how many left over, so q to the n minus x. And then we got an expected value, or mu if you prefer, came out as np, probability of success on each one times how many you have. Followed intuition, nothing too strange going on there. And then our variance, or sigma squared if you prefer, came out as npq. And then so of course the standard deviation is the square root of that. So for example, say we were given something that's binomial, so we do a thing 25 times. When you're writing down your solutions, it's a good idea to say which distribution are we using, and then what am I going to plug in for all my variables. So say we're doing something 25 times, and say it says the success for each time probability is 0.7. Well, then for us, our shorthand is, okay, then my q is going to be 1 minus that, or 0.3. And then say the first question was, what's the probability that we get 12 successes, say? Well, in our notation, that'd be just little p of 12, which is going to be 25. That's how many we're doing. Choose where the 12 successes happen. Our probability of each of those successes is 0.7, and we've got 12 of them. Our probability for each of the failures is 0.3, and we've got 25 minus 12 of them, which would be 13. And then, of course, if you need to use a calculator to do that, I don't have a calculator up, so let me fix that problem. Okay, here we go. So now, to punch something like this in the calculator, I want to do 25, choose 12. The choose would be under math, probability. Choose is the third one here. Choose 12 times 0.7 to the 12. I'm going to put that in parentheses to be careful. 0.7 to the 12. Now let's get out of that exponent to close my parentheses. And then I want to multiply by 0.3 to the 13. Get out of that exponent, close my parentheses. And so this answer would come out as about 0.0115. 0.0115, or 1.15%. Now in your homework, it has some questions where it may ask you for what's the probability of my x coming out between, say, something like 5 and 13. This can be a bit of a pain because for us, that would mean my x either takes the value 5, 6, 7, 8, 9, 10, 11, 12, or 13. And so that would be the probability it comes out as 5 plus the probability it comes out as 6 plus the probability it comes out as 7 and 8 and 9 and 10 and 11, 12, 13. So all the way to the end, and then you would need to add those up. Thankfully, in the examples in your homework, there's not that many, so it's not too time consuming. Another thing that may happen is, and you can save yourself a lot of time, is if it's asking for something like, what's the probability that we take a value that's at least 2? In other words, at least 2 successes. Sorry for my handwriting there. Well, for us, an easy way to do that is that the probability of getting at least 2 is 1 minus the probability of getting less than or equal to 1. In other words, we have 1 minus, and then in parentheses here, the probability that we get a value of 0 plus the probability of getting 1. And this is a lot less computation than if you had to do probability of 2 plus 3 plus 4 plus 5 plus 6 all the way up. So just be conscious that this trick is still handy and will save you a lot of time on your homework. Moving along. So next up we have hypergeometric. Hypergeometric. And for hypergeometric, we were choosing without replacement. So we're selecting, let's say selecting little n many from a population of big N many, where some number of these big N many, let's say big M, are special or distinguished in some way. And then our X is counting the number of special ones drawn. Whoop. Special ones drawn. So our probability function, we just do this by counting. This should be fairly natural for us at this point. How can I get exactly little x many special ones? Well, I would draw little x many special ones and then draw the remainder of what I need to take, so little n minus little x, from the not special ones. Okay, so that's how many ways there are to draw exactly little x many special ones, and then I need to divide by how many ways are there to draw my little n many total. And so on the bottom we have big N choose little n. And then our expected value came out very similar to binomial. If you think of the probability of success drawing a special one on the first draw, then that's kind of like the p from binomial being the proportion of special ones. And so then my q would be 1 minus that. And then our expected value and variance come out very similar to binomial. So for expected value, we end up with NP for the binomial becomes n times m over n. And then for the variance, something a little bit different happens. It looks like NPQ at first, like it was for the binomial. So we have n, but now our p is this big M over n. And then my q is 1 minus that. And then we have this bit of fudginess, this weird extra fraction that comes in, which looks like big N minus little n, and then divided by big N minus 1. And before I referred to this as the finite population correction. So you just have to remember when I'm doing hypergeometric, my expected value and variance formulas look very much like they do for binomial, except there is this bit of fudginess, this correction that happens in the variance. Okay, next up we had geometric. Okay, so for a geometric, we had independent trials. Like for binomial, similar setup. Except now we don't have a limit to the number of times we're going to repeat the trial. Instead, we're going to repeat it until we get a success. So what a random variable is going to count is the number of failures before the first success. Now, it's really important you remember you're only counting number of failures before that success. So if your success is happening on the 20th trial, then your little x is actually 19. So that's something we have to be careful about. And then for the formulas for that, we had our probability formula would just mean I fail this little x many times. Well, if my probability of failure is q, then that means I fail little x many times, and then I succeed right at the end. So we get this probability function. Our expected value, we put a little time into figuring out what this is, comes out as q over p. And then our variance came out as q over p squared. And then we generalize geometric a bit. The geometric is a special case of the negative binomial. Except now our x is counting number of failures before the rth success. In other words, we're doing r many geometrics. And it's also important to pay attention to, we're only counting number of failures the way we develop these formulas. So that can be a little bit tricky. We'll do an example right at the end. Okay, so what were the probability formulas for that? So my p of x came out as, okay, we're counting the number of failures before some final success. Well, there's a lot of ways that could happen. So first I need to say, well, how many ways can that happen? Well, where did my previous successes happen? So I had r many successes total. One of them happens at the end. I have to decide where the r minus 1 other successes happen out of how many spaces are this. Well, if my little x is how many failures, we have that plus these r minus 1 successes. So we have x plus r minus 1, choose r minus 1. And then we're going to fail how many times? Well, that's what our x is counting. It's counting the number of failures. And then we're going to succeed how many times? Well, we have this r minus 1 many that happened here, but then this last success has to happen at the end. So we'll have a p to the r right there. Okay, so we did all that. For expected value and variance, once you understand geometric, those are actually quite easy. For expected value, we just have the expected value for the geometric, which was q over p, except we have r many geometrics, so it would just be rq over p. And then for variance, my variance for the geometric was q over p squared. So now, since this is just R many geometrics added together, my new variance is just going to be RQ over P squared. Now again, it can be a little bit tricky to use a negative binomial, so let's do an example of that really quick. So let's just make one up real quick. Say probability of success for each trial is 0.7. We'll just do that again. What is the probability that the 10th trial is the 4th success? So this is the kind of question you can run into where you would want to apply negative binomial, and it can become pretty tricky to decide what are the values of each of my variables. So let's think through that really quick. Okay, so as always, it's a very good idea when we're writing down our answers to these things to say exactly what distribution we're using and exactly what values we're assigning to the variables. So here, this is going to be a negative binomial. With, now, what is my probability of success here? Once again, we just said 0.7. My Q would be 1 minus that, so 0.3. And now we have to be careful. The probability that the 10th trial is the 4th success. Okay, so I'm counting up to 4 successes. That's my R. If we look back, it's the number of failures before the rth success. So we're doing R being 4. And now, if I'm doing 10 trials up to 4 successes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that last one is a success, and then there's 3 more occurring before that, which means my number of failures that I would be counting would be 1, 2, 3, 4, 5, 6. So our X here is actually 6. And so then I would just say, okay, what's the probability of 6 failures? That would be X plus R minus 1, so 6 plus 4 minus 1. Choose R minus 1, which is 4 minus 1. And then we fail that X many times, sorry. We fail X many times, so 0.3 to the 6, and then we succeed 0.7 R many times by the end, so 4 here. Notice that our number of trials was 10, and these two numbers add up to 10. That's very helpful to remember. And then this number is previous trials except for the last one, so that should be 9, which it is, and this is previous successes, not counting the last one, so that should be 3 since our R is 4. So everything checks out here. And then of course, simplify this down, so we have whatever 9 choose 3, 0.3 to the 6, 0.7 to the 4, and then you can punch it into a calculator just like for binomial. Hopefully that helped. Good luck on your homework. The 3.4 homework is due Friday still. 3.5 and 3.6 homework. Because of all the delays making these videos, I wanted to give you a touch more time, so that's going to be due Monday. I'll give you the weekend to catch up on that. And then finally, the written homework. These are WebAssign homeworks up here. The written homework number 7 is still due Friday. Thank y'all.